To study the vapor-liquid equilibrium data for Cellosolve acetate and toluene. VLE of Cellosolve and toluene system. Abstract, isobaric vapor-liquid equilibrium data for pure components as well as binary mixtures of Cellosolve AcetateToluene was generated using a modified ebulliometer. Measurements are reported for 4 different pressures in the range of 61 to 101 kPa. Pure component vapor pressures were correlated using the Antoine correlation and compared with the literature data. Antoine constants are good match with literature and predicted data. Keywords: Cellosolve acetate, toluene, VLE, vapor liquid. 1. Introduction. Phase equilibria, vapor liquid equilibrium. Distillation occupies a very important position in chemical engineering. Distillation and chemical reactors represent the backbone of what distinguishes chemical engineering from other engineering disciplines. Operations involving heat transfer and fluid mechanics are common to several disciplines. But distillation is uniquely under the purview of chemical engineers. The basis of distillation is phase equilibrium, specifically, vapor, liquid, phase, equilibrium, VLE, and in some cases vapor, liquid, liquid, phase, equilibrium, VLLE. Distillation can affect a separation among chemical components only if the compositions of the vapor and liquid phases that are in phase equilibrium with each other are different. A reasonable understanding of VLE is essential for the analysis, design, and control of distillation columns. Vapor-liquid equilibrium, VLE, is a condition in which a liquid and vapor phase are in equilibrium with each other, a condition or state where the rate of evaporation equals the rate of condensation on molecular level such that there is no net vapor-liquid interconversion. A substance at vapor-liquid equilibrium is generally referred to as a saturated fluid. For a pure chemical substance this implies that it is at its boiling point. Such VLE information is useful in designing columns for distillation, especially fractional distillation. Experimentally investigated equilibrium. In binary system, Cellosolve AcetateToluene. VLE data on binary mixture of organic compounds are of significant importance for the design of numerous industrial chemical processes or for the purpose of environmental protection. In the plants of various branches of industry, where organic solvents are used, spend mixtures from a flow of toxic liquid wastes whose discharge into the environmental is unacceptable. This makes necessary the development of technologies for recovering the starting solvents from the wastes and recycling them, for which phase equilibrium information is necessary. VLE studies of those systems are the goal of the present study. Following systems have been studied. 2-ethoxyethanol, Cellosolve, acetate pure component. Toluene pure component. 2-ethoxyethanol, Cellosolve, AcetateToluene, binary system. This binary system finds application in esterification reaction and reactive distillation. The vapor-liquid equilibrium, VLE, of this system is difficult to model especially due to high boiling point and no data is available in the literature on this aspect to the best of my knowledge. Experiment PTX data of 2-ethoxyethanol, Cellosolve, AcetateToluene system are generated for 8 different set of composition at 5 different pressure for each set of mixture and this experimental data are used to regress activity coefficient model parameters which are further used to generate PTXY data. Results are compared with GE-based models, Margules 2 suffix, Margules 3 suffix, NRTL, Van Laar, Wilson model. GE-based modeling. Isobaric VLE data for the binary mixture of 2-ethanolethanol, Cellosolve, acetate, toluene have been generated. The experimental data were correlated by using GE-based models, Margules 2 suffix, Margules 3 suffix, NRTL, Van Laar, Wilson model. 2 vapor pressure models are used for the given system. For Cellosolve acetate and for toluene Antoine equation is used, whose constants are fitted to experimental vapor pressure. By using regressed parameter bubble T is found out. Activity coefficient model parameters are regressed using experimental PTX data. Then experimental binary PTX data modeled to find vapor phase composition using regressed parameters and compared the vapor phase composition and temperature with bubble T calculated data. B. GE-based modeling. Isobaric VLE data for the binary mixture of 2-ethoxyethanol, Cellosolve, toluene have been generated. The experimental data were correlated by using GE-based models, Margules 2 suffix, Margules 3 suffix, Van Laar, Wilson, and NRTL equations. The experimental data were correlated by using the following GE-based models. Margules 2 suffix model. Margules 3 suffix model. Van Laar model. NRTL model. Uniquewit model. Vapor pressure was calculated using the Antoine equation. Parameters were regressed using the above-mentioned models for all the binary mixture data, and using them, bubble T or the bubble temperature was estimated. Experimental PTX data are modeled to find vapor phase composition using GE-based models with regressed parameters. Activity coefficient model parameters are regressed using experimental PTX data. Then experimental PTX are modeled to find vapor phase composition, and the comparison of the vapor phase composition and temperature with the calculated bubble T data was made. GC parameters. GC parameters. Conditions. For result and discussion. Pure component and binary VLE data for toluene, Cellosolve acetate system have been generated using a differential ebulliometer with a provision of drop counter. The parameters of the Antoine equation for pure components have been regressed from the experimental data. Similarly, the parameters of various GE-based models have been determined by regression using BUBLT calculations. Experimental PTX data generated in this work are reported in Chapter 3. The above system is modeled using various combinations of activity coefficient models, and Table 5.1 shows pure component P/T data. Table 5.8 shows regressed parameters of activity coefficient models. Parameters are regressed at experimental PTX data generated in this work. The compositions reported are in terms of mole fraction, with components 1 and 2 being toluene and Cellosolve acetate respectively. Activity coefficient model parameters of Margules 2 suffix, Margules 3 suffix, Van Laar, NRTL, Wilson parameters are regressed at experimental PTX data generated. Bubble T calculations performed by GE-based models are reported in Table 5.4, 5.5, 5.6, and 5.7 and plotted in Figure 5.4, 5.5, 5.6 and 5.7. Add of experimental and model predicted bubble T is calculated and tabulated in tableaus. 5. Conclusion. The experimental work in this project involved generating pure component and binary VLE data for Cellosolve acetate, 2-ethoxyethyl acetate, toluene. The purpose of taking up this work was that 2-ethoxyethyl acetate is synthesized by the esterification of 2-ethoxyethanol and acetic acid using reactive distillation. To increase the yield of the product and minimize energy consumption, toluene is added as an entrainer. This makes the knowledge of VLE of the species along with toluene also necessary. The data for the above-mentioned system was generated at 4 different pressures. The conclusions drawn from this study are given below. 1. Vapor pressure data for toluene and Cellosolve acetate were generated at 4 different pressures ranging 61.32 kPa to 101.325 kPa. Antoine constants for both the species were regressed using Excel. 2. Experimental, predicted and literature values of vapor pressure for toluene and Cellosolve acetate match.